I'm Jane Huang, a Sagan Fellow at the University of Michigan. I'll be sharing my recent work on detections of spiral structure and CO emission around the T-Tauri stars Ru Loop and Giamaraghi. I would first like to thank the organizers for putting together this virtual conference, as well as all the people who contributed to the work I'm discussing, particularly the teams from the D-Sharp and MAPS ALMA large programs. ALMA has provided extraordinary insights into the structure and evolution of protoplanetary disks. Images of disks at very high spatial resolution, such as these from D-Sharp, have shown that the millimeter continuum emission in disks often trace highly organized and axisymmetric ring structures, which may signify the presence of giant protoplanets. Of course, millimeter continuum emission doesn't tell the whole story about disk structure. These are three views of the same protoplanetary disk, TW Hydra, in scattered light millimeter continuum and 12CO, and they're all shown to scale. And below these images is a diagram showing the vertical cross-section of a disk. TW Hydra's millimeter continuum emission is comparatively very radially compact because it traces the distribution of millimeter-sized dust grains, which decouple from the gas and drift inward toward the star. The scattered light signal is much more extended because it traces the distribution of submicron-sized dust grains, which are much better coupled to the gas. And finally, CO emission, which is also a gas tracer, is the most extended because it remains optically thick out to large distances, whereas scattered light signal falls off rapidly with distance from the star. TW Hydra is often treated as the archetypal disk, but it's becoming increasingly evident that other systems can behave very differently. For example, the millimeter continuum of Ru Loop looks quite similar to TW Hydra insofar as they both feature a series of axisymmetric gaps and rings, but the CO emission is quite different. Ru Loop is a T-Tauri star in the Lupus II cloud, and it is most famous for its unusual photometric variations from UV to infrared wavelengths. The CO emission reveals multiple irregular spiral arms stretching out to about 1000 AU. And note that these images are not on the same scale. The white box that's drawn over the inner region of the CO emission shows you the relative sizes of the scattered light and millimeter continuum images. Now this next slide shows the three images to scale, and we can see that 12CO reveals much more complexity in the planet-forming environment than is obvious in either millimeter continuum or scattered light. 12CO also reveals much more complexity compared to the optically thinner 13CO and C18O isotopologues, which we observed simultaneously. The 13CO and C18O emission are much more compact and largely trace the Keplerian disk. Meanwhile, the large-scale kinematics traced by 12CO are highly non-Keplerian. The Keplerian disk extends to about 120 AU from the star and is then surrounded by some broad non-Keplerian emission out to about 250 AU. And then several spiral arms stretch out to about 1000 AU, and they are blue shifted from the systemic velocity. And beyond these spiral arms, we see a set of clumps out to about 1500 AU, and they're generally red shifted from the systemic velocity. More recently, as part of the MAPS ALMA large program, we serendipitously discovered that the Giamaraghi system shares some striking similarities with Ru Loop. Giamaraghi is a T-Tauri star in the Taurus star-forming region and hosts a well-studied transition disk. Much like most other disks imaged at high resolution, the millimeter continuum exhibits a series of gaps and rings, while the 12CO emission is far more extended and asymmetric, revealing a few spiral arms, diffuse emission north of the disk, and a tail on the southwest side. The intensity-weighted velocity map traces the Keplerian disk out to several hundred AU, but then the kinematics become more irregular in the vicinity of these extended gas features. So what are the origins of the complex gas features that we see around Ru Loop and Giamaraghi? While spiral structures observed in millimeter continuum and scattered light in other disks are often attributed to planets, planets don't explain the large-scale non-Keplerian kinematics that are seen toward Ru Loop and Giamaraghi. These spiral structures might remind you a bit of the CO structures that have been observed in some systems proposed to be undergoing a stellar flyby, such as AS205 or UX tau. Unlike these systems, though, Arulupa and Giamaraggi do not have other stars that are known to be in close proximity. But perhaps Arulupa and Giamaraggi are interacting with their environment in another way by continuing to accrete material from large scales, similar to younger embedded systems. ALMA observations of some of these younger systems have shown that the large dust grains are distributed in nearly axisymmetric gaps and rings, while at the same time, molecular line emission traces larger scale filamentary or spiral-like structures. And the resemblance between these younger and more mature systems suggests that some of the processes that we most often associate with early stages of star formation can continue relatively late into a disk's lifetime. To understand how the environment influences the disk populations overall, though, and therefore planet populations, we need deep 12CO surveys. So far, ALMA disk surveys have generally only observed 12CO for a couple minutes, or not at all. And so they're generally not sensitive enough to trace the kinds of complex structures we are now seeing in Arulup and Giamaraggi, which were observed by ALMA for a few hours each. To summarize, we detect spiral structures and other complex gas features in CO emission around the T Tauri stars Arulup and Giamaraggi. The gas looks surprisingly different from the axisymmetric multi-ring millimeter continuum emission that traces the distribution of large dust grains. It is becoming increasingly clear from ALMA CO observations that the planet formation environment is more complex and dynamic than implied by dust observations alone. Existing constraints on the range of possible gas morphologies are mediocre and need to be improved via deep molecular line surveys of disks. And finally, published data shown in this talk can be obtained at my research website. Thank you all for watching.